Hi everyone, this is Jake Joy. I'm the Immunohematology Reference Lab Manager at Life South Community Blood Centers, and welcome to the lecture on blood components. Today we'll talk about all of the different uses for a blood donation. We'll talk about all of the different things that you can manufacture and make out of a single blood donation. How some of those components are changed and modified, manipulated. We'll also talk about their storage conditions and then finally transportation, what it actually takes to get them to a hospital and finally successfully into a patient and hopefully have a good transfusion, a good outcome. As we all know by now, blood is a very complicated tissue. There's a lot going on. There's a lot of different cell types. The fluid that blood is suspended in or that makes up blood, the plasma contains a lot of different proteins. It's got antibodies. It's got clotting factors. There's many different things going on in blood, and not all of them are what a patient necessarily needs. That's where component therapy comes in. We need to separate out the individual parts of blood, the individual components, the ones that a specific patient needs for their specific problem or deficiency or disease state or a bleeding disorder. Whatever a patient has going on related to hemostasis, we have a blood component, a part of the blood that is best suited to serve their needs, to be that treatment. And that's the heart of component therapy. Is we want to take just the portion of blood that a patient needs and give them just that. They don't need the extra fluid or the extra cell types that are not going to be therapeutic for their case. Component therapy allows us to specifically target and specifically treat what a patient has going on without all of the extra parts of blood that are not needed. It makes the best use of a single blood donation, and then of course it keeps you from wasting the other parts of the blood that the patient doesn't need. They can go to another patient. That's the heart and the sort of the philosophy of component therapy. Whole blood. So whole blood is what you generally think of as when you think of a blood donation. You stick a needle in the donor's arm, they fill up a bag with blood. That's whole blood. That's their blood in its entirety. It's got all the fluids, it's got all the cell types. Everything is there. It's whole blood that goes into a bag that has got some anticoagulants in it and a little bit of preservative. Mainly, whole blood is not used directly for transfusion. Primarily we're going to use whole blood to process further and manufacture individual blood components. And so we've all seen a tube of blood sit in a tube rack, and over time gravity will help it to separate out into different layers. Basically, during component manufacture, we're going to take advantage of these different densities, but we're going to accelerate things. Of course, we're not going to just sit there and wait for them to separate. We're going to use a big centrifuge and spin them down, and then we can separate the blood by its density gradient and then target the individual portions of blood. As you can see here in the picture, you've got plasma at the top. Depending on whether or not we hard spun it or soft spun it, there may be platelets suspended in that plasma. There's a little white layer in the middle. That's the white blood cells, and of course the smallest and the most dense are the red blood cells, and they are down at the very bottom of the bag. But this crucial step, the centrifugation and separation by density, is that's one of that is the key step in component production in whole blood, where then you can express the top fraction away, and this device you see here that is squeezing the bag of blood. Basically, that's what you do. You put it into the expressor, and then you squeeze off the less dense, the top portion, into a separate bag, and then we can seal them away and separate just the parts we need. We can put the platelet-rich plasma or the plasma and later come back and separate out platelets. There's multiple strategies, and it all just depends on the needs of the institution. But the underlying tenet here is that we're gonna separate these things based on density in a centrifuge, and then, for lack of a better word, squeeze off, express off the component that we're interested in, and now we can have them in separate bags, add our other preservatives, and then further process. Once we've got them separated, we can do a lot of different things, and we'll talk about those individually here in just a few slides. One interesting thing is that recently, in the past few years, trauma institutions are more and more using whole blood for emergent transfusions. Usually these are type O whole bloods. Sometimes we do a titer to make sure they don't have high levels of anti-A and anti-B. But in certain situations where a patient will need all of the components of blood at once, mainly a trauma, a whole blood transfusion is the best option. This is relatively recent. Used to be really common, then it went away, where component therapy was the focus. But now we're starting to lean back towards, in certain situations, using a whole blood transfusion. So things always change, and that's just part of the neat part about being in this industry. Apheresis is another collection method that allows us to sort of forego some of the component manufacturing steps. In an apheresis procedure, you can draw the equivalent of 1 unit of blood, 500 milliliters or so, from the donor. This instrument in the picture here, it processes the blood that's been removed, and it separates out and removes just the portion, the component of blood that is targeted in the procedure. The instrument keeps the donor's blood anticoagulated, and after it's been separated and the component of interest removed, the rest is returned to the donor, so that really they're only donating the exact portion of blood, the exact component that we wanted in the procedure. Aside from the advantages of not having further manufacturing steps down the line after collection, we have the ability to harvest multiple components. You can get more platelets out of a apheresis donation than you can out of a whole blood donation. There are not very many platelets in the plasma of a whole blood donation. But in an apheresis procedure, you can target just platelets, and you can get a large therapeutic dose. And in a donor of sufficient mass and platelet count, you can get up to 3 therapeutic platelet doses out of a single donation, which is a huge advantage. And platelets are the most common apheresis procedure. But we can also target RBCs, and you can get a double unit of red blood cells off of a single donation. And there are also procedures for collecting plasma. So apheresis is very versatile, and a lot of times the donor handles an apheresis procedure very, very well, and you save on you don't have as many manufacturing steps after the collection. So a lot of advantage to apheresis. It's a very, very useful tool in the modern blood bank. Okay, so what are the different blood components that we're interested in, and why? What are their functions? Here's a pretty quick breakdown of the main components and what we're interested in. Red blood cells. This by far is the most commonly thought of portion of blood. Those RBCs, we use those to restore oxygen carrying capacity, whether or not it's just through anemia or cell destruction due to sickle cell disease, or to a trauma where someone is actively bleeding. When a patient has a reduced oxygen carrying capacity, a red blood cell transfusion is the solution. Platelets are used in patients that have thrombocytopenia, basically a low platelet count. When your platelet count drops low enough, then a patient will start to spontaneously bleed. You'll bleed from the gums and mucous membranes. Having an adequate platelet count will prevent unexpected bleeding. So in certain patient populations, cancer patients specifically, and there are other reasons for a low platelet count. But anytime that your platelet count drops to a dangerous level, that's when a platelet transfusion is necessary. That's why we produce platelet components. FFP, or fresh frozen plasma, and we'll get into the manufacturer and what that actually means a little bit later. But basically, it's got the full complement of clotting factors. This is it's frozen very soon after collection, and it preserves as many of these plasma proteins as possible. I mean, it does provide for some volume expansion, but primarily FFP gives the full range of clotting factors, and is a really good source of those plasma proteins. Cryo is a very small volume product. It's actually made from FFP, but it's just a small portion of the full profile of clotting factors, but it's got a couple of them in high enough quantities. The AHF, it's anti-hemolytic factor. It used to be used for hemophilia A. It's not as common for that now, but it can also be used as like a gel to put onto a wound and help to seal it up. Some people call it like a glue, but it does have a clotting ability that's a pretty neat product. Liquid plasma is it's never been frozen. Typically, you can store it longer. It doesn't have the same clotting factor advantage, but if a patient is bleeding and they need some volume expansion, liquid plasma may be the component of choice. It's commonly seen in trauma hospitals. And recovered plasma is it's an unlicensed product that it's not for transfusion. Usually this goes to a manufacturer who may make plasma derivatives, or different isolated proteins. The plasma that is not used for transfusion in a blood center, if it doesn't meet our strict qualifications for FFP or other blood components, a lot of times that will get converted to recovered plasma, and rather than discard it, it's able to go to a fractionator, and they can make a useful blood derivative out of the recovered plasma. Let's talk about red blood cells. RBCs, as we know, that's the cell type, that's the component that primarily pops to mind when we think about a blood donation. So when you make an RBC component out of whole blood, there are a couple of things to keep in mind. Uh, First, the whole blood must be anticoagulated. You can't let it clot and turn into a big solid chunk. So all collection bag types and everything's going to have some sort of anticoagulant and preservative to help it keep it from, clotting up into a big solid gel of red goo. Um, there are several different anticoagulant types. Each of these anticoagulant preservative types has its own advantage to what can be manufactured later and other components produced. And of course, they also have different advantages to shelf lives. CPD and CP2D, both of those get you, just with the anticoagulant preservative, a shelf life of 21 days. If you use the enhanced CPDA1, that blood can be stored. It's got a shelf life of up to 35 days. Now, 35 days is pretty good, but there are additive solutions that are more complete mixtures. It's more complete preservative that you can use with. You can't use those an additive solution with CPDA1, but you can use it with CPD and CP2D. And even though CP2D has twice as much dextrose as CPD, it still they both can benefit from the use of an additive solution. And with an additive solution, you can really extend the shelf life of an RBC. You can get up to 42 days with AS in the United States. So some of the examples, AS1, AS5 for CPD, and AS3 for CP2D. These additive solutions just go on the red cell, on the RBC component. The anticoagulant preservative solutions, the blood is collected into a bag with anticoagulant preservative. So when you do a donation, you've got CPD or CP2D in the bag, and the blood flows into the bag. And then after it goes for further manufacture, the blood is spun down, separated, and then the additive solution is applied just to that RBC portion. So the RBCs at that point have been anticoagulated with a little bit of preservative, and then they also get an additional additive solution to extend the out date to 42 days. This is also the point during component manufacture that leukoreduction filter will be used. Depending on the production method, it can happen with the whole blood or the individual, the separated RBC component. But either way, it's going to go through a leukoreduction filter to remove all of the unwanted white blood cells. RBCs can also be collected with an apheresis procedure. You get to skip all of the spinning and separating during post collection. That happens actually on the apheresis instrument. The advantage here is that you actually can collect a double unit of RBCs with a longer deferral period. You have to wait. Normally, you have to wait 8 weeks. If you do a double red, then you have to wait 16 weeks before the next donation. But the advantage, most people don't donate every 8 weeks, so a double unit of red cells on an apheresis collection is usually a good idea. The apheresis procedures are generally pretty flexible, so that you can take an RBC unit and a platelet unit, or an RBC and a plasma. There's several different combinations that make apheresis a real advantage. Your apheresis RBCs are also going to be leukoreduced, after collection. And all apheresis RBCs will receive additive solution and have a 42-day shelf life. Platelet components. So let's first talk about the platelets that we derive from a whole blood collection. This is not as common as an apheresis platelet, but in the modern blood bank, there's still a place for whole blood derived platelets. One of the most important factors in making a platelet component from whole blood is that the platelets must be separated from the whole blood within 8 hours of the collection. After the collection ends, the whole blood is held at room temperature. There are actually some methods that are not commonly used here, but you can cool the whole blood, actively cool it. But the main point is that you take the whole blood from body temperature and you start letting it cool down, whether it's at room temperature or in a cooling device, but it must not go below 20 degrees Celsius. Many blood donations occur on bloodmobiles, and those are not temperature controlled environments. So the regulation on the platelet is to have it cooling towards 20 degrees Celsius, but just not go under, because storage conditions in a bloodmobile especially are difficult to maintain. But a whole blood derived platelet, a single platelet is a pretty small volume, and it does not have very many platelets in it. So most whole blood derived platelets are combined into pools, and that's where you take several platelets of the same blood type. You sterile dock those together into a single final platelet bag that approximates the platelet dose that you find in one single donor apheresis platelet. Apheresis platelets are what we most commonly think of when we think about a platelet donation, and then of course a platelet component. You get far more platelets from an apheresis collection than you do from a whole blood collection. You can even get multiple platelet products, components, therapeutic doses from a single apheresis platelet donation. It is the best way to provide a good high dose platelet product for a patient. If the collection goes as planned, the platelet component will not contain WBCs. Platelet components, we do want them to be leukoreduced, but this is not done by filtration. It's actually a part of the collection, and the platelets are separated without getting into the buffy coat layer. We don't get into the WBCs during a successful apheresis procedure, so you get a good WBC-free platelet component. The risk of bacterial contamination is always there with platelets because of their room temp storage, and the chance for bacteria to proliferate is there. So we must culture all of our platelet components and give them time to incubate and ensure that or be as sure as possible that the platelet components that we're sending to the hospital are not contaminated with bacteria. There are different timing strategies for when to take your cultures, and it will result in either a 5-day platelet expiration or a 7-day shelf life. It just depends on the needs of the institution which strategy they adopt. But the takeaway is that you've got to take a culture from your platelet component to ensure that it is not bacterially contaminated. Fresh frozen plasma. So whether it's derived from whole blood or apheresis, basically it's going to be treated, and we can expect the same for FFP, regardless of the collection method. Main thing is that FFP must go in the freezer within 8 hours of collection. And that's to preserve the function of some of the labile clotting factors. These are clotting factors that will not persist. Their activity won't persist if you allow them to remain at room temperature for very long. Factor VIII and fibrinogen are the main ones here. FFP has to be stored at -18 degrees Celsius or colder. You've got to thaw FFP. You've got to thaw it warm, so 30 to 37. If you don't thaw it warm, then you will get some of the clotting factors, and some of these proteins will precipitate out, and you'll end up with a chunky plasma. So you've got to thaw it warm, and then it's good for 24 hours. As long as you store it refrigerated. After 24 hours, it becomes another product called thawed plasma, which has a shelf life of 5 days. But that first 24 hours is when you have the best, you preserve the most function of your clotting factors and other plasma proteins. Cryoprecipitate AHF. I was telling you about the chunky plasma. The cryo is deliberately made chunky plasma. You thaw an FFP at a cold temperature, and then you will get these cold insoluble proteins that they'll precipitate out. And once they have clumped together, you can then centrifuge the thawed plasma, and these cryoprecipitates will go to the bottom. You can express off the remaining plasma, now the cryopoor plasma, and then you end up with a very small volume product that is a concentrated dose of the cold insoluble proteins that are in the cryoprecipitate AHF. When it's time to be used, a cryo unit should be thawed in a warm water bath, and then it needs to be transfused immediately. If not immediately, then it can be held at room temperature for up to 6 hours, unless it was pooled. If you pooled your plasma or your cryoprecipitate and you did not use a sterile connecting device, then you've got just a 4-hour out date. Any room temperature product that's become an open system automatically gets a 4-hour expiration time. Cryo is it's QC'd to have a certain amount of factor VIII and fibrinogen. It's also got von Willebrand factor, but the main targets here are factor VIII and fibrinogen. If not used for transfusion, it can also be used as a wound sealing gel in places where suturing is not really possible. Think like the surface of a liver. That's a very hard surface to try to repair with sutures, but you can apply the cryo gel to a bleeding liver and get it to seal up and hopefully achieve hemostasis. So what about all that plasma that doesn't make it into the freezer within 8 hours to become FFP? Well, there are several different varieties. We go through the list here. PF24 is very similar to FFP. I mean, it didn't make the 8 hours, but it was frozen within 24 hours. It's in many respects, it's very similar to FFP. The way you treat it and after you store it, thaw it, all that's the same as FFP. A thawed plasma is either an FFP or a PF24 that did not get used in that first 24 hours. After it's been stored for a full day, for 24 hours, refrigerated at 1 to 6, then you have to convert it to a thawed plasma, and then you get 4 more days for a total shelf life of 5 days. Liquid plasma, this was never frozen. As long as you separate it from your whole blood, at any time during storage, and then refrigerate it, it's good for 5 days after the whole blood's expiration date. So whole blood can only separate it with the anticoagulant preservative, this is not an additive solution bag. This is or product component. This is a whole blood that would have had a 21-day expiration date. So if you take those 5 days added to that, you've got 26 days. So we're talking about CPD, CP2D. You don't have the same clotting factor activity as you do in an FFP, but mostly these are used in trauma settings where some volume and some we need some extra fluid to pump. That's where a liquid plasma comes in handy. And then a recovered plasma, this is a plasma that is going to the fractionator to make a plasma derivative. The plasma that's left over after making cryo or plasma that was held too long and didn't make it into PF24 or FFP, that will become recovered plasma, and it goes to manufacture. Beyond the standard component manufacturer, there are some other modifications that we will do to a blood component. Once they're separated and made into their individual components, certain situations require additional modification steps, and we'll go through those here. The first and the most common one is leukoreduction. We've got to remove the WBCs. There's just not a good therapeutic use for WBCs in these other components. And not only do they not provide an advantage, there can be some disadvantages. Think about febrile non-hemolytic transfusion reactions. We have got to get the WBCs out of there. Usually that happens just within the first 24 hours of collection, but it must be, the filters require it to happen within 5 days. Cryopreservation of RBCs is something that can be done. Typically this only happens with rare RBC components, a donor that's got a phenotype that is uncommon. That's when we're gonna think about freezing an RBC. In all cases, you use glycerol as a cryoprotectant. It prevents the formation of the large ice crystals that will pierce and destroy the red cell membrane. Once a RBC unit is frozen, it can be stored for up to 10 years. It must remain below -65 Celsius. Usually this is done in a -80 freezer. That way, you don't get transient warming just by opening the door and raise the temperature above -65. When you thaw a frozen RBC, it needs to be done in a 37-degree, typically a water bath, but there are some other methods with warm beads and things. But you thaw them warm, and then you go through a washing step to remove that glycerol. This typically results in an open system. You have to spike the bag and add saline, things like that. So once we have an open system, the shelf life is is reduced. Since it's a cold product, you get 24 hours while stored at 1 to 6 degrees Celsius. There are some methods that allow for a closed system to be maintained. In those cases, you actually get a 14-day out date when you store it refrigerated. That's a distinct advantage with shipping and trying to get a rare RBC to a patient in the allotted time. Irradiation is another common modification to a blood component. This is done on any component that may contain lymphocytes. If it's a cellular component and might have some residual WBCs, even after leukoreduction, then it's a candidate for irradiation. A lot of times you do this for things like HLA matched platelets, platelet cross matches. If you have a directed donation where there's a relation between the donor and the recipient, that's when you want to irradiate the blood component. In fact, it's a requirement for HLA and platelet cross matched platelets. But the point is to destroy the DNA, the replicating ability in those lymphocytes to prevent transfusion-associated graft versus host disease, which has a terrible outcome. The mortality on transfusion-associated GVHD is very, very bad. But the irradiation, either through gamma or X-rays, will foul up the spelling in the DNA of the lymphocytes, and they're no longer viable. There's some radiation requirements that have got to be met. You've got to hit the unit to the middle of the blood unit. It needs to receive at least 25 grays and no more than 50, and then the minimum dose to any part of the blood component is 15 gray. Irradiation does change the storage life. Your expiration date changes. After irradiation, you get 28 days on your blood component. If you irradiated the unit late in its shelf life, then you may end up using the original expiration date, or if you did it on day 2, then you're going to expire that unit on 30 days instead of 42 days. But it's 28 days after irradiation or the original expiration date, whichever is earlier. Pooling. Sometimes we pool. In fact, commonly we pool blood products, multiple components from different donors into a single pool that will achieve a therapeutic dose. Cryo and whole blood derived platelets are the ones that are most commonly pooled. Both of these, because they're going to be stored at room temperature after the pooling, have an expiration time of 4 hours, unless it was done sterilely. If you had a way to combine and pool these, say with a sterile docker, then you can stick to the original expiration date for both of those components. Washing is done to some cellular blood components, mostly with RBCs. Platelets are sometimes washed also, but in either case, the objective is to remove plasma proteins for patients that have got a history of allergic reactions. Patients that are deficient in IgA will frequently produce an anti-IgA, and in those cases, these patients are going to need to receive washed components. That way, it removes the donor IgA, and it will prevent a transfusion reaction. RBCs that are washed are going to expire in 24 hours due to the open system, and platelets, because their room temperature, will expire 4 hours after the wash. Pathogen reduction is a modification that's becoming more and more common. This is it's a way to inactivate pathogens, really anything that uses DNA. In a blood component, right now we're just approved to use clear components. There's some pathogen-reduced platelets and pathogen-reduced cryo. Trials are currently underway for red cells, and that's being explored. But in either cases, basically, no matter what the pathogen reduction technology is, there's the addition of a chemical and then usually illumination with UV to disrupt the DNA in either a traditional pathogen or perhaps some emerging pathogen that we're not even that's not even on the radar yet. That's where pathogen reduction really shines, because you don't have to test for it. You just no matter what's in the blood component, you can use the PRT the technology and eliminate the risk from the transfusion. Storage and transportation of blood components. So one of the things to keep in mind is that the storage requirements are usually more strict than the transportation requirements for a blood component. Those are going to be different values. The technical manual has a great table that goes through each blood component and their requirements for both storage and transportation for each one. All of our blood storage devices must be continuously monitored, and if you don't have the ability to continuously monitor the temperature on a device, then you have to manually record the temperature every 4 hours. So the different blood components sort of break down into categories. Think about your liquid cold, your liquid room temp, and then frozen red cells, and then frozen plasma. And those all kind of fall into certain categories. So your liquid RBCs, whole blood, liquid plasma, those are all stored at 1 to 6 C. And then during transportation, you're allowed a 1 to 10 degree range for transportation. Anytime you're transporting a liquid cold product, you must do that with wet ice. That is water ice that's in the process of thawing. You can't take a bag of ice and stick it into a -80 freezer and then pull that out and stick it in a blood box, because you will freeze your blood product. You'll freeze your component solid. It's got to be wet ice that is loose and it's wet to the touch and is in the process of thawing out. That will maintain your storage, or excuse me, your transportation temperature of 1 to 10. Your frozen RBCs have got to be stored below -65 degrees Celsius. Typically we do this in a -80 degree freezer, and then during transportation it's got to maintain a frozen state. This is typically done with dry ice, which will hold it at -80. But yeah, keeping it frozen, it's not allowed to thaw out. No, it can't get slushy. Those are the transportation requirements for a frozen RBC. Platelets have got to be stored in a pretty tight range of 20 to 24 degrees Celsius, basically a comfortable room temperature with continuous gentle agitation. You've all seen a platelet rocker. It just rocks the unit back and forth. It keeps those platelets moving in the plasma while at room temperature, and it keeps them from getting activated and clumping up. When you transport a platelet, the technical manual states that it should be kept as close as possible to 20 to 24 degrees Celsius. So it can be outside of that range, but maintaining room temperature is a difficult thing, even with a large insulated box. So they allow you a little bit of leeway. You can only transport for up to 24 hours. That's the time limit for how long a platelet can go without agitation. And then your frozen clear products, your FFPs, your PF24s, the cryo, those are all stored at -18 degrees Celsius, and they must maintain a frozen state during transportation. They don't there's not a requirement for a temperature range. They just must remain frozen, which for our case, this means we ship them on dry ice. Storing blood components is not without its drawbacks. Remember that all blood components those cells are living living cells. They're undergoing cellular respiration. They're using up their available food sources. They're producing waste, and these changes over time have an effect on the blood component. These changes are collectively referred to as the storage lesion. It's just a change over time that happens to a stored blood component. Given enough time, some of these changes are irreversible, which of course will be that sort of dictates the ultimate shelf life on a blood component. But the changes that occur over time will make the intended use of the product. Its intended use could be diminished. So, for example, an RBC that is getting on in shelf life may not give the expected increase in oxygen carrying capacity within the first day or two after it was transfused. Now those cells, they are alive and they do rebound and regain their function, but it takes a little bit of time, and that depending on the needs of the patient, that may be not what's indicated at the time. That they may need a more immediate increase in oxygen carrying capacity. So there are some things requirements that may be requested, as in a fresh unit for, say, pediatric uses or sickle cell patients, to avoid the drawbacks that we experience with the storage lesion. And here's a sort of a breakdown of the changes that you can expect with prolonged storage of blood component. This is a summary of the storage lesion. There's some things to expect. You've got your living cells. They're going to use up their ATP. So that the ATP levels will drop, 2,3-DPG will drop. You're going to get a decrease in pH, an increase in potassium. Free hemoglobin will increase. Just be mindful of these changes, and think about what's going on during storage. And a lot of these will make sense, and so just be aware that these changes do occur in stored blood, and that sometimes when a hospital requests fresh units for a certain patient population, that they have their reasons, because the storage lesion can affect outcomes in certain patient populations, and it makes sense to be aware of that. All right. Any questions? This concludes our overview of components. Hopefully you've got a good idea of what it takes to get from a blood donation, from collection all the way through to a transfusion. If you've got any questions, feel free to get in touch by email or Slack, and I'll be happy to answer them. Thank you.